Alright, what's up guys? Welcome back to another video. In this video we're going to learn about Bayes' rule, Bayes' theorem, and the law of total probability. So Bayes' rule is a rule that gets used a lot. This is still, in the realm of conditional probability, but where in the previous video, we were given an event happens followed by another event. Now this is those two events but flipped. So now we're given event 2 happens first, and then we have to find event 1. So what I mean is, instead of the probability of B given A, now we're asked to find the probability of A given B. And that looks like this. It still has the same form as the original equation, where on top you have A intersect B, but now down here you have the probability of B. And if we wanted to extend this form even more so that we see each individual part, then that looks like this. Times the probability of A over probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. So, maybe you'll remember this bottom section from whenever we were doing the question about the urn, where you have to find where you're given, either we chose urn 1 or we chose urn 2, and then we have to find the total probability of that scenario, which is this P of B right here. And then this top part, is just like the rewritten form of this, basically. See? Like whenever we're asked to find the intersection in those questions, but we are given the conditional probability and then the total probability. But this is Bayes' theorem. And actually, there's a much longer version, but that comes in later. But yeah, so how do we use this? Well, there's a a 4-step rule that we can use in order to find this probability of A given B. So I guess in like a general question, or maybe like most questions, step 1, right? We are given A, the probability of A, and the probability of B given A. And okay, so if you're going to try and solve a Bayes rule question, this is just one way to do it. And so let's say we're given A, the probability of A, and the probability of B given A. Remember, this is the event, the probability of that event happening, and the probability of event B happening given event A. So if we're given this, then we can safely assume that the probability of B intersect A is equal to the probability of B given A times the probability of A. Right? And again, this just comes from the previous rule, but also you'll notice it's very similar to this top part, other than the fact that these two events are switched here in the intersection. But again, B intersect A is the same as A intersect B. So we can write this out, right? So if we're given these two, then we can find this. Now, step 2, say we're given A complement, the probability, hold on. The probability of A complement and the probability of B given A complement. Then again, just like here, we can also say that the probability of B intersect A complement is equal to the probability of B given A complement times the probability of A complement. So again, say we're given these two terms here, then we can find this intersection, the probability of the intersection. All right. Okay, step 3. So now that we have these two probabilities of these intersections, now what we can find is that the probability of B is equal to these two intersections added up. And you know, like in the Venn diagrams, whenever you have, this would represent that middle part where both circles intersect, and then this would represent that part of circle B where it does not intersect with A. It's like the remaining of the circle B. So, you know, the probability of all of B would be these two terms added up together. Right? So now we have the total probability of B. And then, well, we have the total probability of B now, and we also have, we found the intersection of B intersect A or A intersect B. We'll look at that. That completes this expression up here, because now we have this numerator part and we have this denominator part, which can now give us the probability of A given B, or Bayes' rule, or Bayes' theorem. So the last part, or the last step, would be to construct this so that we have the probability of A intersect B over the probability of B. Well, that's equal to the probability of A given B. And that's what we were trying to find. This right here. So, and again, you can only do this if you're given some information, which I think will happen here in a second. Okay, yeah. So it's another example involving urns and the white and black balls. But yeah, so this is how you could solve this, and I'll show you an example. Alright, so we have this problem, this example. Earn 1 has 2 white and 2 black balls. Earn 2 has 3 white and 2 black balls. So that's like the other example, kind of. One ball is chosen at random from earn 1 and transferred to earn 2. Then a ball is chosen at random from earn 2, which turns up white. Find the probability that the ball transferred from earn 1 to earn 2 was white. Okay, so this scenario has 2 events. So the first event is the transferring of the ball, right? From earn 1 to earn 2, so that would be event A. And the second event, event B, is that we chose the ball from earn 2, which turned out to be white. So what we need to do is find the probability of A given B. So what's the probability of, what's the probability that the ball that we transferred from earn 1 to earn 2 is a white ball? Okay, so I'll write that up here. So event A is the event from the ball from going from earn 1 to earn 2. And then event B is we picked up a ball that was white. All right. So, okay. So again, from the 4-step, process that we just did, we can say that the probability of A, so we have A, and then we need to find P of A. Well, we're given this already. We just have to kind of read through the lines or read between the lines to try and figure out what P of A and P of A complement is. So in this case, the probability of A is the unconditional probability that the ball we chose from earn 1 is white. So basically, like if I close my eyes and I choose a ball from earn 1 to move, that ball is either going to be white or black. And because there's 2 white and there's 2 black balls, then there's a 50-50 chance of getting either a white or a black ball. So so the probability of A would be, me closing my eyes, picking a ball, and it's white. So again, the probability of A is 1/2. And similarly, if I close my eyes and I pick up a ball to move and it's black, or the probability of A complement, that is also 1/2. Again, because there's 2 of each. Alright, so we have A, we have probability of A, and we have the probability of A complement. So now, let me see if I can sort of explain what I wrote here. Okay, so if we close our eyes, chose a ball from earn 1 to earn 2, and it was a white ball, then that means that earn 2, instead of having 3 white balls, now it has 4. And that means that if I, again, randomly chose a ball from earn 2 to pick up, and it's white, well, because now there's 4 white balls, and there's 6 in total now in earn 2, then now I have a 2 over 3 chance of choosing a white ball. And that would be the probability of B given A, right? So I guess I'll kind of draw it over here, maybe. So we have earn 1 and we have earn 2. So if we chose a white ball to put in earn2, then yeah, because earn2 had 3 white balls and 2 black balls, well, now there's 6 balls in total. So now we have a 4/6 chance or a 2/3 chance of choosing a white ball from earn2 as the second event. So yeah, so 2/3 is equal to the probability of B given A. So I guess I'll write that here. So B given A is now equal to 2/3. All right. And I'll put here that this is move, or hold on, maybe not move because we don't move it yet. So this 1/2 is equal to picking a white ball to move. And this 1/2 is picking a black ball to move. All right. And this probability of B given A, again, is just equal to us picking up a white ball, or us picking a ball randomly for earn2, and it happens to be white, now that we've moved the white ball, which again is 2/3. Okay, but what about if we did that same whole process and we instead of us moving a white ball over, it turned out to be a black ball? All right, well, then that would be the probability of B given A complement, right? Because A complement involves the black balls. So I'll draw that down here. If we move the black ball over from earn1 to earn2, well, this still has 3 white balls, but now this has 3 black balls. So that means that if we transferred a black ball from earn1 to earn2, and then we chose a ball from earn2 and it happens to be black, well, that's a 1.5 chance. That's a probability of 1/2 that we chose a black ball. So P, the probability of B given A complement, is 1/2. All right. Okay. So now we pretty much have everything that we need, right? If we go back to the process, we have A, the probability of A, and the probability of B given A. We also have B, the probability of A complement. Excuse me, hold on. Okay. Sorry, let me start over. We have A, the probability of A, and we have the probability of B given A. And in this case, we also have I guess A complement would technically be like the choosing of a black ball, right? I mean, we don't even really use like A complement by itself to like in the calculation. It's more of just like a signifier, I guess. So what we do need to use though is probability of A complement and the probability of B given A complement. So for step 3, you know, we would find the probability. Well, first before we get to step 3, let's find the intersect probabilities, because we need those in order to find the total probability of B. So, okay. And if you'll remember, the probability of, okay, so now we're on to, we're still kind of like in step 1 and 2, because first we were just trying to find each individual like probabilities here to use for steps 1 and 2. Okay, so step 1 for real this time is we have to find the probability of B intersect A, and this is equal to the probability of B given A times the probability of A. So B given A is 1/2 times the probability of A 1/2, so that's 1/4. Alright? And then we have to find the probability of B intersect A complement, which is the probability of B given A complement times the probability of A complement. And B given A complement is 1/2, and A complement is also 1/2. Guys, I messed up. I'm so sorry. This is not 1/2. B given A is 2/3. That is my bad. Okay, so 2/3. Sorry. 2/3. This is right though. Probability of A is 1/2. So 2/3 times 1/2 is 1/3. Well, it's 2/6, which is 1/3. Okay, this one actually, the probability of B given A complement is 1/2 times the probability of A complement is 1/2. So this one is 1/4. Hope you can see that. 1/4. Okay. I'm gonna erase this right here. Because now we can do step 3, which is we find the total probability of B, which is us just adding the 1/4 plus the 1/3. So step 3, to find the probability of B, we add the probability of B intersect A plus the probability of B intersect A complement. So B intersect A is 1/3 plus B intersect A complement, not 1/2, 1/4. And that is equal to 7/12. Alright. So, yeah, we find the total probability of B, 1/3 plus 1/4, 7/12. Now we have this right here, the probability of B intersect A, which is the same as the probability of A intersect B, 1/3. And we have the total probability of B, which is 7/12. So now we can find the probability of A given B. So step 4, the probability of A given B is equal to 1/3 over 7/12. And that is 4/7. And that's our answer. Yes. So, yeah, this is an example of Bayes' theorem, where you have to, like I said, just from like the question, from reading the question, you have to sort of be able to find this stuff, like up to here, all this up, and yeah, it just takes practice, you know, like to be able to identify identify, like what P of A is or what P of B given A is. But yeah, I mean, once you have that, then the rest of this is just, it's 4-step algebra. So it's not too hard, but definitely like identifying these is like the hardest part. Okay. Let's do another example. Ivory Coast is winning. Sorry, I'm watching Ivory Coast Germany. I didn't even see them score. Oh, I think because they just scored. Nice. I think it was Frank Kessier. It was. Okay. We'll do another example. This one involves a set of twins. Okay. So, identical twins are the same sex, while fraternal twins have a 50-50 chance of being the same sex. The probability of a fraternal set is P, and an identical set is Q, which is equal to 1 minus P. If the next set of twins are of the same sex, formulate the probability that they are identical in terms of Q. Okay, so just like the previous example, we need to find the events A and B. So, let me see, how do I want to... Okay. So, in the... Dang, that's twice. So in the previous example, we had that event A was the event of going from one ball from urn 1 to urn 2, and then event B is us picking up that ball. So we'll do kind of the same here. So the first event that we could look at is let's see. The probability of a fraternal set is P, and an identical set is Q equals 1 minus P. If the next set of twins are of the same sex, formulate that they are identical in terms of Q. Okay. Okay, so I'll solve this one a little differently. This is like another method I guess we can use, and it's in a chart form, so I'll show you. But for this instance, let's say that B is the event where the set of twins are the same sex. Same sex. And A is the event that the set are identical. All right. So again, we're still trying to find the probability. In all of these, we're still trying to find the probability of A given B. Okay, so again, we go through the question and we see what information we can take. So now we have these two events, right? Okay, so what is the probability of A? What is the probability that the set of twins are identical? Well, that is given to us because in the problem it says an identical set is Q, which is equal to 1 minus P. So the probability of A happening is Q, which again is equal to 1 minus P. Okay. And what is the probability that they are not identical? Or what is the probability that they are fraternal? Or excuse me, hold on. Do I want to say it like that? Yeah, okay. Yes, because in the question it says the probability of a fraternal set is P, which would be the opposite of identical twins, right? So, okay, so the probability of fraternal twins is P. And again, that was given to us in the question. All right, so we've gotten two bits of information out of this question already. So what about the probability of B given A? Because that is also one that we were asked to find in the previous question, which we could do here as well. So yeah, what is the probability that the set of twins are the same sex given that they are identical? Well, if we go back to the question, identical twins are the same sex. So there's a 100% chance that that is true. If two sets of twins are the same sex, then clearly they have to be identical. So the probability of B given A is 1. It's 100, but again, we could just say 1. So I'll write that over here. So the probability of B given A is equal to 1. Right? I think I said it backwards just now, but given the set of twins are identical, they have to be the same sex. Identical twins are the same sex. Again, that's from the question. So that would be 1. All right? What about if given the set of twins are not identical, what is the probability that they're the same sex? Which would just be, I guess, fraternal twins, right? And I mean, if we go back up to the question, fraternal twins have a 50-50 chance of being the same sex. So that means that the probability of B given A complement is 0.5. So it's half the probability of B given A, because fraternal twins have a 50-50% chance of being the same sex. So yeah, the set of twins are not identical, then what's the probability of them being the same sex? Again, 50-50 chance, so 0.5. Okay, so boom, look, we've already got pretty much everything we need. Like I said, it's just a matter of parsing through the question and trying to make sense of what they're telling you. That's the hard part. So, okay, now what we have to do is find those the intersection probabilities, right? So yeah, so what's the probability of B intersect A? Well, remember that that's just the probability of B given A times A. The probability of B given A times the probability of A. And that would be, let me see, how do I want to, times A, which is Q. Okay, yeah. So, all right. Oh, also, just to, again, reiterate this fact, the question asks us to find the probability in terms of Q. That means that our answer at the end has to have the Q variable. So we're not going to get an exact number answer, but we need to find the answer in terms of Q, and hopefully that will become clear as we go through the question. So, okay, so again, the first step is we find the probability of B intersect A, and that is the probability of B given A times the probability of A. So B given A, that's just 1, okay, that's easy, times the probability of A, which is Q, which is equal to 1 minus P, but we want the answer in terms of Q, so that's where we'll just use the Q. Okay, so this is just equal to Q. All right, step 2, the probability of B intersect A complement is equal to the probability of B given A complement times the probability of A complement. B given A complement is just 0.5, and then the probability of A complement is P, but we want the answer in terms of Q. So let's look at this this part of the problem right here, which is the probability of A. All right, so if we want this answer in terms of, if we want the probability of A complement in terms of Q, because right now it's just P, but we want to make this in terms of Q. So here we would just solve for P. So what we would effectively do is, and I'll write this over here actually, Q is equal to 1 minus P. So we would solve this for P, and we would subtract 1 from both sides to get Q minus 1 is equal to negative P, and then we would multiply both sides by negative 1 to get that P is equal to 1 minus Q. All right. What this lets us do now is, instead of putting just a P right here, because we're trying to solve in terms of Q, now, like I said, instead of putting P right here, we can now write 1 minus Q. And that keeps us from having to put a P and having 2 variables in our final answer. So P is equal to 1 minus Q. So again, instead of bringing P down here for the probability of A complement, we can write 1 minus Q. Okay, so this is still in Q, and this is still in Q, so we're good, because we want our answer to be in Q. Okay, so step 3 is we find the total probability of B. And that is where we add the intersections. Right? So the probability of B is equal to the probability of B intersect A plus the probability of B intersect A complement. So B intersect A is Q plus B intersect A complement is 0.5 times 1 minus Q So I just got rid of the multiplication sign right here. So now it's just, you know, next to each other in parentheses form like this. So we can distribute this 0.5 to the 1 and to the minus q. So that we have q is equal to 0.5 minus 0.5q. And if we subtract half a q from a whole q, that gives us another half q. So we have 0.5q plus 0.5. All right? And also, I mean, we can just take a 0.5 out from both of these terms, from the 0.5q and just the 0.5 by itself, and that will equal 0.5 times q plus 1. All right. We're almost done, because now the only thing that's left is step 4, to just put it all together now. So I'll erase this like top part right here. Okay, so step 4 is we just put it all together. So the probability of A given B is equal to the probability of A intersect B over the total probability of B. So again, A intersect B or B intersect A, same thing, is Q up top. And then the total probability of B, we solved all the way down here, which is 0.5 times Q plus 1. And we want the answer in terms of Q, which we did. So that is the answer. I said I was going to do it in chart form. I lied because, well, I didn't want to, I guess, like throw too much at you guys and at myself. But, yeah, so I just went ahead and I did it the regular form, you know, the 4-step process. But yeah, so this is our answer. And again, I feel like the hardest part was just trying to identify the information. But we were able to get there at the end, right there. Okay. The next thing we'll look at is an extended form of Bayes' rule and Bayes' theorem. So the one we did, this 4-step process is just like the simplified version, but there is a much longer, I guess more in-depth version of this. So I'll show that. All right. All right. So this is like, I'm looking at it right now. I'm looking at my notes, and the easiest way I can try to explain this is like, if we have like, so just now in these past examples, we only had 2 events, right? Where we had one thing happening followed by another. But this just involves more events. So, here, I'll write it out and then I'll kind of explain it. So, we have Well, first it's showing us the general law of total probability, which, I mean, if you think about it, the general law of total probability, that would just be like us adding up all the probabilities to get to 1. Right? So, really what that looks like is like this. Okay, so if we have event B, the probability of event B is equal to the sum of all intersections of the probabilities of B intersect A sub I, where I goes from 1 to n. So, okay, yeah, so the probability of B is just equal to the sum of all of the intersections between B and all of the events I that go from 1 to n. And that can also be written as the total sum of the probabilities of B given a sub I times the probabilities of a sub I, where I goes from 1 to n. And this is just like what we've been doing, right? You know, obviously the intersection is equal to the probability of B given A times the probability of A. And this is just like a general form where we have way more event A's, or yeah, just like more events to consider, I guess. So yeah, I mean, obviously, you know, we've been doing this. This is just, we're just adding up all those probabilities to get the total probability of B. And of course, this same idea, the same concept applies to the extended form of Bayes' rule, where instead of having 2 scenarios, now we have like 3 or more, you know? So, and again, this is the general law of total probability. General law of total probability. That is this. And if we wanted the general form of Bayes' theorem, well, that is equal to the probability of A sub j given B is equal to and I'll just write it out like all extended, is equal to the probability of B intersect A sub j times the probability of A sub j over the sum of the probabilities B given A sub j times the probability of A sub j, where j goes from 1 to n. So yeah, I mean, this is just something we've already been doing. It's just we're including more events now. You know, in these past examples, it's only been 2 events, but now, yeah, this is like 3 or more. So, okay, let's say we have 3 events then. Let's say that this j goes from 1 to 3. So n is equal to 3. Then that would look like, I'll start at the top. The probability of B given A sub 1 times the probability of A sub 1, and all of this over the probability of B given A sub 1 times P of A sub 1 plus the probability B given A sub 2 times the probability of A sub 2 plus the probability of B given A sub 3 times the probability of a sub 3. So yeah, that's what this extended form looks like. So yeah, this summation, like I said, is just a shorter way of having to write all this out. And yeah, like I said, here we have, you know, 3 or a couple other events to look at. It's not just A and B. Now it's B, A sub 1, A sub 2, A sub 3. So it's like, yeah, it's like I said, it's just more events. And this this is gonna be useful in this next example. Okay. So right now it looks like a lot, but like I said, this hopefully makes sense in this example I'm about to show. So it's another die example, but now we have 3 dice. So 3 dice have the following probabilities of throwing a 6: P, Q, and R. One of the dice is chosen at random and thrown. Each is equally likely to be chosen. A 6 appeared. What is the probability that the die chosen was the first one? Okay, so instead of 1 die, now we have 3. Okay, and in what I just erased in the extended form of Bayes' theorem, remember we had a sub 1, a sub 2, a sub 3. So because we have 3 dice to choose from, those would be our event A. So let's say that a sub 1 is the event that the first die is chosen. And then a sub 2 is the event that die 2 is chosen. And a sub 3 is the event that die 3 is chosen. And then our event B, which is separate from us choosing the die, is the fact that we threw a 6. Okay, so event B, a 6 is thrown. Right. Okay, so okay, so remember that we were also given probabilities that if you threw a 6 from die 1, the probability of landing on the 6 is P. If you threw a 6 from die 2, the probability of landing on a 6 is Q. And if you threw a 6 from die 3, that would be R. The probability of that happening would be R. So okay, we have to use those probabilities as well. So considering all of that, in order to find the total probability of B to use to find the probability of A given B, well here, first let's find their intersects, because that's step 1 from the 4-step process. Okay, so step 1, we find the probability of B intersect A. In this case, it would be A sub 1, right? Because we have to consider all of these. So so step 1 is we find the probability of B intersect A sub 1, which is just the probability of B given A sub 1 times the probability of A sub 1. So the probability of B given A sub 1, that is equal to P. again, let's take a look at this. What is the probability that we throw a 6 given we chose die 1? Well, again, in the question, that probability was just P. So that's what this is. The probability of B given a sub 1 is P. Now, what is the probability that die 1 is chosen? Well, there's 3 dice to choose from. If we choose any one of them, it's going to be a 1/3 probability. So that is 1/3. All right. And we use this same logic to find B intersect a sub 2 and B intersect a sub 3. So the probability of B intersect a sub 2 is equal to the probability of B given a sub 2 times the probability of a sub 2. So what's the probability that we throw a 6 given that die 2 is chosen? In the question, that was Q. And what's the probability of choosing die 2? That's 1/3. And finally, the probability of B intersect a sub 3 is equal to the probability of B given a sub 3 times the probability of a sub 3. What's the probability that we throw a 6 given die 3 is chosen? It's R, letter R, times 1/3. Okay, so this one might have been a little easier. I don't know. It's up to the person doing the problem, but I mean, we were able to find all these intersects already with the information we were given. So now, normally, step 3 would be to find the probability of B, which we'll just go to that. We won't call it step 3. We'll just keep going using that 4-step. In this case, it'd be kind of like a 3-step process, but okay, so right. So let's find the total probability of B. And that would just be us adding up all these intersects. So we have that the probability of B is equal to this, P times 1/3, plus Q times 1/3, plus R times 1/3. All right? And we can simplify this a little bit. Since we're multiplying all of these by 1/3, then we could write this in this form. P plus Q plus R over 3. Right? So P times 1/3 would be the same as P over 3. Q times 1/3 is the same as Q over 3. And R times 1/3 is the same as R over 3. And since we're adding up all of these terms, we can just add up the numerators and have them over the same denominator, which is 3. All right. And that's how we found the total probability of B. Now the last step would be to find the probability of A given B. All right. And in the extended form of Bayes' theorem, it would be the probability of A sub 1 given B, and, well, what was A sub 1? Hold on, let me actually keep writing this out. So the probability of A sub 1 given B is equal to the probability of, what is it? It's A sub 1 intersect B over the probability of B. Because, well, that's just Bayes' theorem. And what this is equal to is, where is it? Right here. So P times 1 over 3, right? Because the intersect, again, if they're switched, they're still the same thing. p times 1 over 3 over the probability of b, which is all of this, p plus q plus r over 3, p plus q plus r over 3, and this can actually be simplified a lot. Here, let me rewrite this top part. So remember what I said, if you multiply like this p times 1/3 is the same as p over 3. So we'll write that. Okay, this is too many fractions. This doesn't look very good. So we can clean this up a little bit. And we can just take the reciprocal of both p over 3 and p plus q plus r over 3 and have I mean, we just flip these. So what this ends up looking like is, actually, how about instead of flipping them, we just I mean, how about instead of flipping them, we just multiply each thing by 3. So that way we can get rid of this 3 in the denominator, right? And it wouldn't even really change anything. Okay, maybe it'll be a little more obvious if I write it actually in its original form. So p times 1 over 3, and this is equal to p plus q plus r times 1 over 3. Okay, now it's maybe a little more obvious. We have 1 over 3 in the numerator, we have 1 over 3 in the denominator, so those just cancel out. And what we're left with is p over p plus q plus r, and that is the answer. So again, we still ended up using that same 4-step process, but there was no a complement to solve this time because we have more than just 2 events, right? We have 3 dice to choose from. So we have to find each individual intersection from each die, and then at the end, you know, to find the total probability of B, we add up those intersections, we get this, and then at the end, what we're trying to solve for in the extended form of Bayes' theorem is a sub 1 given B. And that a sub 1 is very important, especially when you're doing extended form. If you were just doing the simplified version of Bayes' theorem, then this would just be written as a given B. But in this extended form, I didn't write it very well, but this is a sub 1. There's a 1 right here. Yeah, a sub 1 given B. And that's why that P went up top right there. P times 1/3. And also why it ends up as our numerator here in the final answer. But yeah, so this is just like Bayes' theorem, like I said, just a more extended form. So that's it for this one. Oops.